Okay, we can get started. Good morning. It's a fairly smaller class today. So before we start, so we had 25 people filling out the survey, right? And so if you look at the question, sort of like you have like a big chunk of the people who believe we are going at the right pace, right? There are a few who think it's kind of going slow, few who think it's going fast. So I think as a general average, this is sort of fine, right? But that doesn't mean that the people who are on the either end should be left out. So if you think it's going too fast, let me know how we can add additional material. And if you think it's going too slow, let me know how we can add more material. So one of the ways I can add material without actually taking the class time is through that video. So I don't know how many of you actually saw the one on GDB, right? I'm trying that for the first time, and I want to see how that works. And for me to prepare that is kind of weird because I'm just sitting in my office talking to the camera, and I'm not so used to, because there's no human beings, and I have no idea whether it's useful or where it's going, right? So things like looking into kernel code, some of you commented that you like to look into, that may be a better way for me to go through them. I can go through them at some pace. You can go through them at whatever pace you like, and you're not forced to. I mean, that's not part of the curriculum or whatever. So if you're interested in some topic, I'm not promising I'll get to that immediately because it does take a lot of time because I need to have 2 cameras set up and all those things. But it can be done in that way. And so most of you think the course is going like this one, going at the right pace. Few of you think it's going slow, and few of you think it's going fast. But if you're on either ends, let's see how we can work this out. And this question, I just wanted to see what people thought, on what is your view on operating systems, right? It's not related to the course or what have you. And many of you don't want to see anything else beyond this course, right? The majority doesn't want to see anything more. And that's a little unfortunate because one of the ways I disagree with what Tony talked about when he was here, he was talking about how you should have breadth and all those, like the things you do beyond what you learn in these classes, right? Which is all fine, but the way to enter most of these companies, you go through very technical interviews, right? You'd go through very technical interviews. I think some of you who interviewed at Microsoft and HP and all realize you don't get through the door unless you have very technical stuff, right? It's annoying to the point that if you're going with a PhD and you're going into Microsoft research, you still have to talk to the front people who ask you stuff like, do you know how to write bubble sort, right? So when they asked me, I said, no, I have no idea how to write bubble sort. I have no idea what C is. Because it's kind of annoying because you get irritated because you're like, my thesis was on systems, like we do this for a living, but they don't care. I mean, they still want you to go through the stuff. So they don't feel your pain, right? So regardless of what you go, so HP Labs does that, Google does that. So you could be very good, but you still have to. You're still computer scientists, right? So you still have to know some of the stuff. And some of the things we looked at, like threads and all those things, have very little to do with the operating systems. I mean, they are, it's your program. Use some of the primitives we have, but you still have to understand all those things. So that's one way I disagree with Tony. Yes, it's true. Maybe you'll never write to program anything, but you're still computer scientists when you walk through the door, right? So hopefully we'll change some minds later. Yeah. So going back to the paging, virtual memory and stuff. So do you have any questions so far on what we did on last lecture? Last lecture, we are saying, since we have the notion of physical and logical addresses, we can use the fact that they are separated to move some of these pages off the system, so you can actually create a logical space which is bigger than your physical space, and you can do other tricks such as copy and write and stuff. But essentially, you separate out the notion that every page has to be on the physical memory, right? The way you do that is to move the extra pages to the swap space. So essentially, you may have to find some page, move that to the swap page, and move the page that you want back in here. And the mechanism that you do for that is called page replacement, because you are trying to replace some page with another page. So you have to find a victim page and move it off, right? So the page replacement algorithms would want to reduce the number of page faults, right? The way you can reduce the page faults is if you keep all the pages that you would want to run your program in main memory, then you reduce your page fault. So their goal is to make sure that the pages that you would want should be in main memory. Pages that you don't want should be thrown out, right? Without going to the details of the different policies, what would be your ideal policy that would do that? What do you think would be a policy that will make sure that every page that you want in the future should be in your main memory, right? So our assumption is your physical is smaller than your logical, right? And your program is going through the logical space, and you have to map them into the physical space, right? How would you ensure that all the pages that you want should be there? We have seen some of this when you talk about process scheduling and stuff. What would you
You're good at prediction.
Yeah, you're good at prediction, right? I mean, it helps. If you're Oracle, it really helps. If you know the future, excellent, right? If you know the future, then you can predict what would be needed. Actually, if you're Oracle, you don't have to predict. You know the future, so everything is fine. Many operating systems are not Oracle, so you want to be able to predict what the future is, right? So the more you can predict, the better you can do. And same like process scheduling, prediction, you can't run a very complicated algorithm trying to predict, because you have to balance the cost, right? So if it's really simple, that's good. But if you have to do a whole bunch of effort to predict something, then all the effort you spend in prediction is wasted, right? So you have to balance those things. And this theme runs throughout the operating system, right? For process scheduling, if I know the future, I can do great. But I don't know the future, so I try to predict what the future is. And we're not trying to find the optimal algorithm. We're trying to find an algorithm which is simple enough, fast enough, and does a decent job, right? And those are two things you have to remember. We're not trying to find the optimal algorithm all the time, or the best algorithm. So we don't want to run a data mining algorithm here which runs for half an hour and comes back and says, you should replace these pages, right? Because you want them to be done in milliseconds or microseconds or what have you, right? So those we'll see some of the policies, but the policies would seem obvious once you think about what you're trying to achieve. You're trying to see what should be set in the future. So in order to do the analysis, we usually talk about using reference strings, right? Just like we were doing with the processes with Gantt charts and stuff. Here we talk with reference strings, which basically says that I want to, in the example there, it says, I'm accessing these logical pages, right? And I want to see what the page fault would be for a different policy, right? And if you think about it, this is essentially what your homework project 3 was asking, right? Homework project 3, you take a real system, you get all the address traces, right? So you have to separate out the offset page from the page count, right? So if you separate those out, essentially, so if you assumed a 32-bit address, and your logical address had 10-bit offset, right? Because the page table was 1 kilobyte in the example in the assignment, right? Which means that this is 22-bit, right? So every logical address that your program generates, take the upper 22 bits, and that's your reference string, and that's what you're doing for your homework project, right? And we don't want to have such a long number, so we use a small number here for discussion. So we want to run these things through and see what kind of page fault you want. And ideally what you want is the more memory you have, the less page fault, right? And so if you buy more memory for your system, you want your performance to improve, where the improvement is measured here in reduced page faults. And as we saw in the previous equation, the page fault dominates how much time it takes, because page fault means you have to go to the disk, and disk is so slow that you want to avoid page faults as much as possible. So this is the kind of sort of the ideal graph. I mean, you don't have to worry about precisely how it works, but essentially the more frames you have, the more physical memory you have, you want to have less page faults. And that is not always possible. That's not always how it should happen, but that's what you would like. So here let's look at a simple case, right? The first policy is first in, first out, right? And for a moment, let's ignore how you would implement first in, first out, because you need to figure out some kind of a count, right? So you have to figure out which came in first, which came in next. So you have to keep a counter. Ignoring those, right? So if you have the reference string as 1, 2, 3, 4, 1, 2, 5, and so on and so forth, and if you have 3 frames, right? Essentially, when you start out, it's all clear. There's no pages, right? So you get the first, you get reference for logical address 1, so you put it here, right? And logical page 2, so you put it here, logical page 3, right? And then the reference string goes for logical page 4, right? Which is not here, so we need to run the replacement algorithm. And since we're running first in, first out, this is the first one to come in, so you replace this with 4, right? And then you get 1, right? And 1 was replaced. 1 is no longer here. The first one of the pages to the left is here, so you put 1 here. And then you ask for 2, and 2 is not here anymore, so you replace this with 2, right? And so on and so forth. And if you have 4 frames, right, and you have the number of page faults. So I encourage you to go through this at your leisure. But essentially, in this example, adding more page frames actually cost you to create more page faults, right? So you went from 3 page frames to 4 page frames, and that actually costs you more page faults. So this is the equivalent of you buying more memory, and the system is actually slower because you have more memory, right? And that's called the Bellardi's anomaly. And there's reasons behind it, and which we don't really go into. Essentially, these are the access pattern. If they are stack based, then it causes some concerns like this, right? So if you this actually runs through all the replacements that you can imagine for the long reference string, right? And I'm not going to go through each one of them, but essentially that's what you do. So you kind of do this replacement. So when you're doing this replacement, you can kind of feel what is going wrong, right? But here we replace 4 with 1, right? But then we ended up needing 1, which we just replaced. So we made some mistake because we shouldn't have replaced 1, because that's going to be the one which is going to be used next. But since we didn't know the future, we replaced it. And then we find out that we really needed 2, and so on and so forth, right? And one of the ways that your program can do something like this is the matrix thing, right? So when you run a loop like this, right, when you go through a matrix, right, you end up creating something like 1, 2, 3, 4, whatever your size of the matrix is, and then you end up going. You may end up going through like this because of the loop. You are going through the same data over and over again, and depending on what the size is, you may end up where you keep replacing the last page that ends up being used in the future, right? So these sort of, when you go through this code, your reference string affects you. And that's one of the things I encourage you to look at this stuff. So if you run the pin tool on your different programs, you can see how the memory references are being done. And when you write programs for a living, that's something you want to be aware of. Because if you create the wrong kinds of stuff, OS cannot predict, and you kind of work against what the OS is trying to do, right? So in this case, if you run it through for different frames, so if you look at on the y-axis, the number of page faults you get for different page frames. So from 1 to 2, it's constant at 12, and at 3, it goes to 9, and then at 4, it goes up to 10, and then it reduces, right? So you want to avoid anomalies like this,
So here the anomaly occurs between 3 and 4?
Yeah.
But otherwise there is no anomaly?
No.
Okay.
Yeah, it only happens for some sizes. It doesn't have to happen for all the sizes, but at some point you are working against what the future pattern is, right? So the optimal algorithm, similar to what we did for the page scheduling, is something which knows the future, right? So if you know the future, then we replace it with something that will be used the furthest into the future, right? So this is a sort of, it's an interesting algorithm, right? So again, the string is 1, 2, 3, 4, 1, 2, 3, 4. Now we need something to replace. We need to replace 1, right? Sorry. So yeah, 1, 2, 3, 4, and then you go through 1 and 2, which are used. Now we need to find a space for 5, right? So at this point, we replace it with the page that will be used furthest into the future. So we don't look in the back, in the past, we look in the future. If you look in the future from 5, the next is 1, next is 2, next is 3, next is 4, next is 5. Since 5 is the one which is being discussed, we have to replace 4 because that's the one which is going to be used in the future. So we replace this with 5, right? So if you do that, then the next 1, 2, and 3 will go through, right? And then when 4 comes in, 4 needs a space, and we don't have the sequence further down, and it turns out replacing the 1 to replace it with 4 would give you the best stuff, right? So you can't really implement this because you need the future, but this is a way to see how good your algorithm is. So so for example, in your project, for your homework project, since you have the reference string, you could write a code which figures out what the optimal number of page faults is for a given case, because this is probably optimal. And essentially, since for your homework project you have all the future sequences, you could do that, right? But it's not practical because you can't really know what the future is. And you have the referencing for the whole stuff. We just did for a few pages, but essentially, if you run the whole thing, you know what pages get replaced and how, right? And essentially, you run it through something like this, right? So since we can't know what the future is, we look at the past, just like we did for the process scheduling, to figure out what should be replaced. And the counterpart of the most furthest into the future is the least recently used, right? So the idea is, if it hasn't been used for a while, then we assume that it may not be used in the future, right? Can you think of a case when this would not be the case? Yeah.
Blue?
Yeah, it's right here, right? So in this case, we are going through like this, right? Let's say I'm going through in 5 and stuff, right? So if I'm here, right, the least recently used is 1. And if I'm here, the least recently used is 1. But turns out, because of the loop, the next one would be what was used a while back, right? So if you're going through this loop, LRU is horrible. But in other cases, least LRU may be good, right? So and that is the same theme throughout the operating system, right? You believe that LRU would be good. There are pathological cases where LRU would be horrible. And since you're developing something for the whole system, you try to see, you want to see if the average case behavior is good, not necessarily the pathological cases, right? So it may work poorly for your particular program, but you hope that it will work for all the program. And the way you understand whether it's good is sort of what you're doing for a homework project, which is you develop the string, right? So if you're a PowerPoint developer, you run PowerPoint, you generate all the memory references, then you run it through different algorithms, right? So if you're Microsoft and you find that I can optimize for PowerPoint by using LRU, right? PowerPoint and Word and all the stuff that we sell, if it happens to work with LRU, then that's what I want to do, right? Because then my OS would look really good for those. And you're kind of stuck with what they sell you because that's what you got. And so if you develop a program, it helps if you understand what's going on, right? You don't have the choice to change the kernel, but at least you won't work against the kernel, right? So to implement LRU, you need to know when it was, when a page was used. So you have to keep some kind of counter to see when it was used, right? So it no longer, I can't just keep the pages. I need to keep track of when a page was used at sometime in the past. So some of the ways we implement this is to use the reference bit, right? So the idea here is if the hardware provides a notion of reference bit, which says that within the last clock, this particular page was referenced, right? It doesn't tell you how many times it was referenced. So if you look at so let's say in this case, right? The OS sets up the page like this and lets the process run, right? So it sets all the reference pages counts to 0, right? And the hardware says whenever a page is referenced, it'll tell you, it'll change that to 1, right? So at this clock, if this is what it was and it let the process run, and when the OS gets control back, if it looks like this and this was referenced, right? In reality, this might have been referenced 1 million times, and this might have been referenced 1 time, right? We don't really care. And if it comes like this, that's an approximation which says that in the last clock, these 2 pages were accessed and these were not accessed, right? So we can approximate LRU by saying these are most recently used and these are least recently used, right? It's not precisely saying which one of them was. So it's not order. So the way you order them right now is 2 and 4. 1 and 2, right? These 2 pages were further back, and these 2 were recently accessed, right? Does that make sense? At this point, all I know is these 2 were not accessed, right? And these 2 were accessed within the last clock cycle. If I keep doing this for a while, I have an ordering of pages which approximates what LRU would do, right? It does not say how often something was accessed, but it basically gives you a sort of approximation. And that's implementable because the hardware can provide you with this reference bit, right? If the hardware provides you with the reference bit, this is the way to implement LRU, right? Right? Because anything else would mean that somebody has to keep track of the count and times and stuff, and those all have to be done by hardware. And hardware typically does not provide all that much stuff, because all of them would have to be set up somewhere in a page table or something. So every time you get a page fault, the OS has to go and set all the reference bits to 0 and count how many were turned out to be 1. And then in its own internal data structure, it has to say, in the last cycle, these were modified and these were not modified. And it can keep track of that to see. So in the next iteration, if it turns out only this was modified, right? Then it can say, sorry, this should have been.
The second T should be in 3.
This is, yeah. Yeah, sure, yeah. So this was the first time. In the second time, we would know that right? The most recently used is 3. The one previously used is 1, right? Which was used in the previous clock cycle, but not in the current one, right? And then 2 and 4 we don't know, but they were used before that. Yeah.
Could you walk through the previous example again, the 2413, because I can't follow it right now.
Okay.
Trying to.
So this is 1, 2, 3, 4, right?
Right.
So the first time I go through, right? I set the reference bit to be 0, and when I came back, these 2 were set, right? Which means that within the last time period, somebody made access to these 2 pages and not to these 2 pages, right? Which means that we can say 2 and 4 were accessed 2 cycles back, in the past, and 1 and 3 were accessed recently, right? So least recently used pages are 2 and 4, and then 1 and 3, right? We don't know which order they are, but we know that 2 and 4 was accessed in the past, and 1 and 3 were accessed recently.
Where are you getting the 1 and 0s from in that column? By the
this one?
Yeah.
So that's what the hardware provides, right? So I get the OS gets control. It sets all these to 0. It sets this reference bit hardware to 0, and it lets the process run. So when the OS gets control again, right? If this page was ever referenced, then the hardware would have changed them to 0 and 1, right? So the OS has to go back and see. So it sets all the bits to 0, lets the process run, and when it gets back control, it sees which ones were set to 1, right? And so these two were set to 1. So it infers from that this is what must have happened.
Okay.
These two pages were never referenced, and these two pages were referenced in the past, right? It doesn't say exactly when they were referenced. So we have no way of ordering these two, but at least we know this is the order, right? So I'm saying at this point, the OS would say, we'll reset all of them to 0, let them run, right? So when it came back again, if it turns out if this was how it happened, so at that instant, it will know that it still doesn't know which order 2 and 4 is, but it knows that 1 and 3, right? The most recently used is 3, because that's the one which is set here. In the previous cycle, somebody modified 1. The previous cycle, somebody could have accessed these things. So the LRU algorithm, when it runs, it'll replace one of these, right? For the first, it can choose 2 or 4. It doesn't matter because it doesn't know. And then it'll replace 3, and then it'll replace 1 and then replace 3, right? So that's a way of approximating LRU algorithm just by using the 1-bit counter, right? Right. And again, that depends on what the hardware provides, right? The other way to provide LRU is to use a stack implementation, right? And we'll see what that is in the next slide illustration of it. Essentially, when a page is referenced, right, and we can either do that by setting the page to be for you to get a page trap whenever the page is accessed or what have you, and we move the page which was recently accessed to the top of this stack, right? So essentially, you maintain a stack within the operating system, right? And here, anytime a page is referenced, right, you make it do a page fault, right? So you set the page bits to invalid, right? So when somebody accesses the page, the OS gets a page fault, and the OS would do this manipulation, and then change the page bit to valid and let it go, right? So the manipulation it does is, whatever page was accessed recently, it moves it to the top of the stack. And it replaces stuff from the bottom of the stack, right? So for example, the stack used to be 21074. It's not a real stack because it pulls elements from the middle and puts it on the top, right? So since somebody referenced page 7, right, it pulls the 7 from the bottom and moves it to the top. So potentially the replaceable pages used to be 4, then 7, then 0, then 1, then 2. Now it's 4, 0, 1, 2, and then 7, because 7 was most recently accessed, right? And the cost of doing this is it has to manipulate, I think, 6 pointers, right? Yeah, 6 pointers have to be manipulated, right? Because at this point, if you look at the before stack, right, you have to, the pointer from 0, the next should now point to 4, and the previous from 4 to point to 0, right? So you need to make those things, and then you move the 7 up there, then you set this pointers again, right? Yeah.
So if the reference is in the stack already, you just pull it out and put it on top.
Yeah. And again, you're trying to implement LRU with what you have. Here the hardware did not have a notion of reference bit. All it has is a valid bit, valid, invalid bit, which we saw before. So we set the page to so whenever we get when the OS gets control, it sets all the pages to be invalid, right? When someone accesses the page, the OS gets a page fault, and the page is all valid. So it's just doing this trick to figure out when you access the page, right? So it sets the validity bit to be valid. It sets the stack and lets you go, right? And this is a way for the OS to keep track of which pages are being accessed what. It approximates LRU in some sense, but the OS gets involved every time a page is accessed, right? At least once, right? In the case of the reference counter, OS is not involved at all. It just sets these bits, let you go, and that's it, right? So now you have to manipulate these 6 pointers, what have you. Yeah.
Wouldn't it be better to use like a linked list here, because with a stack, when you're removing the 7 from the middle, you have to change all the things above it. Why?
It is actually a linked list. I mean, that's why I said it's a doubly linked list for the thing, right? It's not a real stack because, yeah, you're pulling some element in the middle. No, so it's a doubly linked list, right? But you're free to choose whatever because now it's in software. It's not done by hardware. All the hardware says is, I got a page, somebody referenced page 7, right? And yeah, obviously you would with that with the linked list, right? Yeah, I don't know why they call it stack because it's you pull an element from the middle of the stack, right? That's not a stack operation. So, so those are some of the things, and you can have more complicated stuff depending on what the hardware gives, right? So this is one of the reasons why the hardware folks should depend completely on the operating system folks to make anything happen, right? If you take any hardware course, and the hardware people have no use for any of these bits, have no reason to say whether it should be bit based or what have you, right? But if they don't implement it right, so if they don't give you the reference bit, OS has to be involved every time it does this page faults. It has to do this counting and stuff. So overall, your system now appears slower because you're doing all this stuff, right? So hardware folks, whether they like it or not, have to talk to the OS folks because they both are a team, right? In fact, there are some conferences which are essentially AS+, which is architecture and operating system. If you look at the protocol stack, right? If you look at the way things are done, hardware folks depend on OSs to get stuff done, and they also depend on the compiler folks to generate good code, right? And OS cannot do anything if the hardware folks don't give you the stuff, so they have to communicate a lot more, right? So when you take the architecture course, pay particular attention to these stuff, because from architecture perspective, you don't really care whether it's reference bit or reference counter or what have you. But from a system perspective, if you don't provide me with the reference bit, then I have to do this stack based or something which slows me down. So you may have a 2 gigahertz processor which may be blazingly fast, but I can't really use it because I have to do these tricks, right? So I hope it's clear. So if you're taking architecture right now, pay attention to why they're doing these stuff. The same for TLBs and stuff, right? TLBs are not used by hardware folks, but they're essentially used by the OS folks, right? So if you don't provide good TLB, then the system will suffer, and the customer would say both of them. They blame both. They blame the hardware and the software because it's a partnership, right? So actually, the hardware can actually provide more. They don't have to give you single bits. It can actually give you multiple bits. As you go up the food chain on more expensive hardware, they can actually give you multiple bits, which still may not be enough for you to count precisely which, so you may have only 3 bits, right? So if you make 1 million hits, you only know that there was 8 hits or whatever, and the OS can use that to make a better decision. It can decide whether 2 or 4 should be kicked out, right? So the last policy is the second chance, which states that we don't really know what should be replaced. We may not actually precisely know what should be replaced. So we'll give a second chance for these pages to be thrown out, right? So it's better with the illustration. Right. So the second chance, or the clock algorithm, has a notion of a clock, and that's the arrow up there, right? It says that I want to look from there to a page that has to be replaced. So we replace the page which has the reference bit set to 0, right? And this is a reference bit that we keep in software. And any page which is brought in has this bit set to 1, right? So if you come under the arrow and you happen to be 1, I set the bit to 0 and then I move on, right? And when I come back on the second time, if you're still 0, then you're kicked out. If the page was referenced between the time that I moved and came back, then the bit is reset to 1, right? So here's what happens. So the victim right now happens to be where, if you look on the left side, where the pointer is, that particular page has a reference of 1, which means it was accessed recently or it was brought in recently. So we set the bit to 0, then move on to the next page, which also happens to be 1. So we set the bit to 0, move on to the next page, and that happens to be a 0, so that will be replaced. So the second from where the arrow is would be the one which gets replaced, which is right here, right? And then you keep doing this, and the arrow keeps coming back to the same page. Before this arrow goes around and comes back, if the page was ever referenced again, the reference bit would go to 1, so it will get a second chance, right? So when the arrow comes to you, if the reference bit is still 1, then you get a second chance. If it's 0, then you get kicked out, right? This is a little bit more complicated, but this essentially says that we may not exactly know what should be replaced, so we're giving you a second chance, right? Is that clear? Yeah.
You have the words next victim written next to the arrow, but the arrow is pointing to something that has a reference bit of 1.
Yeah, so I'm saying, so this arrow goes through in a cycle, right? It goes to the next page and so on, right? So at this point, the next victim happens to be pointing there.
So that page would be thrown out, except it has a 1 there, so it's not going to throw it out.
Yeah.
It'll move on.
It'll set the bit to 0, and it'll move on.
Okay.
And then next one happens to be 1, so it set the bit to 0, and then move on. And then the next one happens to be 0, which means that it was accessed 2 chances back, right? Not just the first chance, but 2 chances back, so that'll be replaced, right? So even though we set the 2 pages to be 0, if the page was referenced, then their value would be reset to 1, so they get 1 more chance before they're replaced, right? So those are the things you can do when you have the notion of bits, reference bits and stuff that you get from hardware. And like I mentioned, you can have more complicated algorithms depending on how much the hardware can support. If the hardware really supports lots of things, if you can support the notion of a counter, you could replace least frequently used and most frequently used, and the power of those systems come depending on how big the counter is. If the counter is 3, then you're not going to be that much more accurate, right? But if the counter happens to be, let's say, 16 bits, right? That means we can figure out which pages are being used a lot. So the problem you're trying to solve is between these two, right? We don't know precisely which one is being accessed a lot. And in the case here, I mentioned that this page was accessed 1 million times, this page was accessed 1 time, and we have no way of differentiating what those are. If you had a way of knowing what this number is, then you can use least frequently used or most frequently used, right? And the reason why we go through these different algorithms is the observation that if I use the least frequently used page, right, which sounds good at first glance, but the problem is when a new page comes in, it's always the least frequently used, right? So if you only implement least frequently used, every page which comes in would be the one which has to go out first, right? So it never hangs around to accumulate enough counts to stick around, right? So most frequently used sounds kind of like oxymoron, but most frequently used balances against that, right? Least frequently used would mean that if a page was used a lot, right, it'll always be in the system regardless of what, because if you're using a least frequently used algorithm, and if a page happens to somehow become most frequently used, it'll never be replaced because it's most frequently used. So even if the page is never used after that, since it's accumulated enough count, it'll still be around, right? So you want to balance that with some notion of a most frequently used or some way of aging these things out, because otherwise, if a page is most frequent, if it is used a lot, then it's always there kind of thing, right? So you're trying to solve one problem, but you may add another problem, and those are the and that's the problem, right? So people, you keep trying different algorithms depending on what the hardware can give you and depending on what you think your program should do. And essentially the way you do that is what you're doing for homework project 3, right? You're trying to see what typical programs are doing, and you're trying to tune your algorithm to fit those things. And you try to get as close to the optimal algorithm, which depends on knowing the future, which in your case you actually know because you have the reference strings, right? So all these cases we talked about, replacing these pages only on demand. And most operating systems don't actually do this when you need a page. So it can go through in some daemon at the back and keep some pages in ready pool, right, ready to be kicked out, which means that if the OS decides that I don't need a page right now, right, but if I needed a page, this is the page that would have to be replaced, right? If it kept that proactively, then it can actually write the contents to the disk, right? Because it can write the contents anytime, but it can do that because it's not doing anything else. So it can keep the disk busy by writing it out. So when you really do need the page, you avoid the cost of writing the page out because it's already written, right? But if you're waiting on the page to be kicked out, if somebody accesses the pages, then it's moved back into the regular pool, right? So it doesn't have to wait till you need something. It can keep track of what pages. So even if it has nothing to do, it can keep writing the dirty pages out to the disk. So when you need the pages, it's right there, right? And that's the notion of keeping the buffered algorithms, because you don't want to wait till the end. You want to keep some amount of pages, right? So the next challenge is who should get how many pages should you have per process, and who should be, where should take the frames, right? So then you have the notion of a minimum number of frames, right? And that depends on the particular hardware. And so the minimum frames specifies how many frames you need for your system to at least complete one assembly instruction, right? Because if you have less than that, you can't even complete that one instruction. Your process cannot proceed, right? So, for example, on the IBM 370, which is a mainframe computer, right? This one particular instruction can actually touch 6 pages, right? So it essentially moves one memory location. I think it moves 2 memory locations to a 3rd memory location, right? And these can span 2 pages. This can span 2 pages. This can span 2 pages. It's a humongous bunch of data being moved, right? So if you run on this machine, you at least have to have 6 frames per page, because if you ran this instruction, right, first you get a page fault for this one, for the source part, right, and you bring those 2 pages, and then you get a page. So you restart the instruction. Then you get a page fault for this, right? Then you move those 2. Then you get a page fault for this. Then you get to find a space. But if you only allocated, let's say, 2 frames for this program, you get a page fault. You find two frames for this. You restart the instruction. You get a page fault here. But since you had only 2, I would have to replace this content with the 2 that I already allocated to you. Then you again get a page fault because now this is failing, right? So instruction restarts, and it gets a page fault again. So it'll go through this. It'll never get restarted, right? Does that make sense? So you have to at least give it 6 frames. The 6 frames are necessary in this program, because in the worst case, if you don't give it 6 frames, this particular program cannot move. It'll keep bringing the page and so on, right? So that's the minimum, right? The next goal is trying to figure out how much to give. And so there are 2 ways of giving pages out. One is fixed allocation, and another is priority based, right? In the fixed allocation, I give equal number of frames to all the processes. So if I have 10 processes, I give each process 1/10 of my physical memory, right? It's simple, but as you can imagine, it's wasteful, right? So if in a system you're running PowerPoint and a bunch of other virus checker and all those things, your PowerPoint gets only as much as the other 9 sort of useless programs. So in the priority-based allocation, you vary it depending on the allocation, and this whole notion of how much to give is not as trivial as as we kind of mentioned in this case, right? Because this is the same as figuring out if I have a certain amount of resources and you have all of you, right? How much should I give to each one of you, right? It depends on what you're doing and how important you are to the system and so on and so forth. And the challenge is the operating system has no way of knowing who or what, right? So if I assume that all of you are processors, then from my perspective, all of you are processors. But from a user perspective, one of you is PowerPoint, which is most important. Another one of you is a virus checker, which is important but not that important, and so on. OS does not know, but how do I communicate that to the OS? That's the problem we're trying to solve, right? So in the fixed allocation scheme, we just divide it among all the people equally, right? It's good because it's simple. It's bad because I can't allocate memory to processors that need more, and I take it away from processors which don't need all that much, right? So if you do the number, you kind of if you do the little equation, you can figure out how much should be given to each frames, but there's no way to take it out. So in the case of a priority-based schemes, you give more pages to higher priority processors, right? And those are not the end of all the stuff, because in a typical machine, all the processors may run on the same priority, right? So you may have to go through more different policies to say, even though PowerPoint and the spell checker are running at the same priority, the PowerPoint may have to have more memory because it's a larger program, right? So that introduces the notion of global versus local. So if I want a new page, do I take it from yourself or do I take it from the global scheme, right? So do I take it from somebody else or do I take it from myself, right? A global scheme is preferable because then I can go and rate somebody who's not that important, which means that process now begins to get page faults for no fault of itself, right? So how do I figure out, how do I steal from one process and give to another one, where I don't destroy the previous process, where I still make progress for the new for the other process? How do I balance globally? How much should each of them have? Who should I take it from? And how do I not destroy the other process? Right? It how we define all this algorithm is basically trying to run your system and tune it for your preferred use. Right? So if you have Microsoft, then you figure out what are the important applications what people run, and how these things are using memory, and try to figure out how to tune Microsoft operating system for Microsoft Office, and so on and so forth, right? So I'm going to stop at this point because we're running out of time. And thrashing is a point where things break so much that you're basically doing page faults all the time. But we'll see that after we get the class, right? So I'm going to make the exam later today. So if any of you want to take it during the break or what have you, contact me, email or drop by or something, right? And it'll cover everything till this point. Yeah. Yeah. Actually, email is preferable than anything else, right? And I will be here on Monday. So the following Monday. So if you want to do it here, I'll be here.